If search feels slow, guessing is not enough. OpenTelemetry shows whether retrieval, filters, embeddings, or reranking are causing the delay. You'll walk away with a setup that traces retrieval, filters, re-ranking spans, and flags the slowest stage. I'm Professor Pi, teaching search and IR with simple Python. Search pipelines hide their costs across several stages. First, you fetch candidates, then you call with filters, possibly call an embedding API, and finally run a re-ranker. When latency spikes, which stage do you fix? Tracing replaces guesswork with data. At its core, OpenTelemetry Search Tracing gives each stage a named span. Spans collect duration and attributes, so your trace links retrieval time, filter time, embedding latency, and re-rank cost together. The upside is direct visibility and simple aggregation. The downside is extra instrumentation and some overhead. So we keep this example small and focused. We will build a tiny Python search flow that emits spans for retrieval, language filtering, a simulated embedding call, and a re-ranker. That keeps the idea clear and maps directly to real pipelines where you already have lookups, metadata filters, and a last stage scorer. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we wire up a tracer so every stage can emit spans. This snippet wires up OpenTelemetry's Python SDK so your search pipeline has a tracer ready for spans. Latency triage stalls when you cannot even capture trace data yet. So we start by installing a global TracerProvider via trace.set TracerProvider. The SimpleSpanProcessor plus ConsoleSpanExporter keep things minimal while still letting you inspect every span in your terminal. By calling trace-get-tracer search pipeline once here, later snippets can reuse the same tracer without reconfiguring providers or exporters. The printed tracer ready, true confirms the tracer exists and is ready to emit spans. With the tracer installed, capture the time spent fetching candidate documents, so retrieval cost is isolated from later work. This example records a retrieval span so you can see how long the initial document fetch actually takes. Cold retrieval hides a lot of latency, so we wrap the lookups in tracer.start as current span retrieve before the list comprehension on documents. Because the span is open only during that comprehension, the computed duration milliseconds reflects pure retrieval cost rather than downstream work. Setting search.hitCount and search.duration MS attributes makes it easy to inspect both the candidate volume and timing in your trace viewer. The printed retrieved docs equals 3 duration MS equals 0.17 shows how many documents matched and how quickly this phase finished. Next, we want to know whether trimming candidates by metadata is cheap or costly compared to retrieval. This code watches the language filter, so you notice when metadata trimming slows the remaining candidates. Filter logic often crawls because of branching dictionaries, so we surround the comprehension with tracer.start as current span. Filter.language. The span captures search.filterlang along with the event built from event data, letting you compare how many hits survived the filter versus how many you started with. Keeping docpop near the filter sets up downstream re-rank math without recomputing lookup tables. The printed filter docs equals 2. Filter mess equals 0.05 tells you the filter kept 2 documents and how long the culling took. After metadata work, the common hotspot is the embedding call. That may be local or an external API. This example traces a simulated embedding request, so upstream spans can tell when external calls dominate latency. Embedding APIs usually sit on another service, So we mark the span with span-kind client and add a small time.sleep to mimic the network hop. The list comprehension creates a tiny vector, while embedding.dim and embedding.latency.ms attributes preserve both the representation size and the measured wall clock time. Because embed returns both the vector and duration, later stages can reuse the timing without remeasuring. The printed embedding dims equals 3 embed ms equals 20.04 shows how many dimensions came back, and the simulated calls latency. Finally, we need to open up the reranker so its internal cost is visible alongside everything else. This snippet wraps the reranker so you can compare scoring latency against earlier retrieval work in the same trace. Re-rankers often become a black box, so the tracer.start as current span, rerank.score block walks through each filtered candidate and mixes docpop, query token overlap, and vector average when building scores. Consolidating the math inside the loop lets you annotate the span with rerank.candidateCount and the final rerank.durationMS, which are the numbers you need to reason about slow rescore calls. Because the function returns both the sorted list and the measured milliseconds, any caller can log, alert, or feed dashboards without recomputing the sort. The printed top rerank ID, doc2, rerank ms equals 0.12, highlights which document won and how long the rerank phase took. In a real project, this toy mapping becomes a one-to-one relationship. Swap ConsoleSpanExporter for a production exporter, and your trace backend will show the same spans, letting SRE or product teams query which stage caused a regression. Recap: this is end-to-end stage tracing for a search pipeline. Spans separate retrieval, filter, embed, and re-rank costs, so you can triage latency across stages or validate optimizations. Use it when you need data to pinpoint slow stages. One caveat is that tracing adds instrumentation overhead, so you should measure sampling and exporter load in production. Next step: tune the re-rank scoring mix between document popularity and vector similarity, and watch how the re-rank span duration and result quality change. That lets you trade compute for precision with data in hand. If short, practical IR helps, subscribe and watch the IR videos.